Welcome, welcome. We're going to be using Visual Studio Code to do test-driven development for microcontrollers. In our case, we'll be using STM32L071, RBT6, I believe, to be exact. So essentially, what you will need are these extensions. We're working on a Windows machine, by the way. We'll have C, C++, IntelliSense. You can have the extension pack as well. We'll have Seedling, the test explorer, Cortex debug as well, and then we'll have the test explorer UI. Okay, that's all you need to install for now. All right, let's quickly open up a folder. Create your own folder at any location you'd like. I have it as test-driven development. You can have it as whatever you want. So this is what we'll have. Right now there's nothing inside. We're going to create everything from scratch. Don't worry about that. So I'm talking full bare mats in here, like everything. You're gonna do everything basically. Make files, link files, everything, and then we're gonna just have everything set up. We'll have, yeah, it's gonna be a long journey, but it's gonna be worth it. Let's get started. So let me quickly explain a few things before we even get started with everything, just so that it makes sense as I'm going along and doing everything. Right, so we have our MCU, your microcontroller, whichever it may be, MSP430, PIC, SM32, whatever it may be, right? And let's say we have some register, RCC underscore CR. It's usually defined in the data sheet of SM32 in this fashion, right? It stores a 32-bit value, okay? And it points to a specific address. And this address, let's just make up some numbers, 0x200, right? It points to this location. So when we do have write drivers for this to interface, it's going to be pointing to this location, right? And whenever we compile the code we write for this microcontroller, we'll be using, for example, ARM non EABI, right, dash GCC. Okay, I hope that's fine. Makes sense, right? Now we have the PC or the laptop. Okay. Now what we need to do is we need to replicate this. So we'll have RCC underscore CR. But instead of pointing to this location, our computer is going to do it by itself. It's going to still contain 32 bits that we'll be manipulating, right? But instead of pointing to that location, it will point to RAM, inside RAM in the PC. So that could be 0x800 or something. Now, as you can see, they are not pointing the exact location. It's not pointing to 200. The thing is, and that the reason for that is that we're going to be compiling it with GCC instead of ARM non-EABI GCC, right? This is compiling for the target. This just compiles for the PC, right? So usually what happens is that inside your MCU, you have to basically, what usually happens is that when you write a driver for GPIOs and you need to you test it by blinking an LED or turning the LED on or off, then you essentially the whole process works like this. You write code, you compile it with ARM non-EAB GCC, and then you upload it to the MCU. Okay? And then if the LED isn't blinking or toggling or whatever, then you usually run a debug session, right? And in that debug session, now you manually go through and check each of the peripherals and see if you configured the clock, the GPIO, if you turned on the clock for that port or whatever it may be. and that can be very cumbersome. Like, it's a lot of work to do that, right? And it's slow and tedious. So with test-driven development, instead of doing it on the target, you're basically going to test all of that you used to do manually a lot all the time. You're going to be doing it right here on the PC. Okay? So by the time you're done writing the entire driver for the GPIO.H and GPIO.C, and you test it on the target, everything will be working. No need to run debug sessions, anything like that. Maybe one or two times you'll be doing it, just to, if in case something doesn't work. But in most cases, you can now test those registers right here on the PC because it's in RAM, right? When you configure this register RCC_CR, it's not in RAM, right? You're just configuring it. It's a physical location, right? But here in the PC, we're creating it in RAM. So if this is 10111, you can actually now just test, hey, is this 1 or 0? It's supposed to be 0. Then make my test fail. Then fail. Fail, bro. So if you change your driver in any fashion, as soon as this was accidentally configured to be 0, you'll be flagged and it fails. It's supposed to be 1, so it fails. So even before you even compile it with this and load it to the target, you already know there are some issues that you need to fix, right? And when you do compilation for this on the PC, it's much faster to execute everything on the PC than it is on the MCU, right? We're working with megahertz here. This guy works with gigahertz, right? Just to have an heads up on that. So essentially, in a nutshell, that's kind of what we're gonna do. So in the header file for STM32, blah blah blah, whatever it may be, .h, you'll have something like you'll be pointing to a specific memory location, which could be that 0x200, right? And when you actually change the value, it would look something like this, right? CR, and then you'd be changing a bit, like 1, in location 2, right? Don't forget the U here. There's a U there, right? In our case, we won't be doing this, right? Because it's already dereferencing and pointing to a specific memory location. In our case, what we will be doing is we'll do some modification in the header file. Like, I don't like this, but you know, that's what I had to do. But if someone finds another solution for that, just let me know. Essentially, what we'll be doing is doing this on the PC, right? This is exactly what we'll be doing. Exactly the same, it's just that we don't point to any address. Right, so we'll just go from this arrow to a dot, right? And in order to accomplish that, we're going to have to go into the header file and do some modifications. A specific header file, right? And then essentially we can create these instances. And now instead of trying, now you know that the MCU was trying to point to this location, right? But let's say this location doesn't exist in your PC, or it actually points to a file. You don't want to be modifying that file. Or let's say that this location points to, I don't know, like your PC might be using this RAM resource already for something else, like, I don't know, to log on to the PC or something. Or maybe a Windows Defender is using it, or some other process is using that location. You don't want to be accessing and modifying it, right? So that's why we're going to do that's why we're not going to point to a specific hardware location. We're going to let the PC decide at which location it's going to store. And for our example, we decided it might be at this location, 0x800 or 8000, you know, or 80,000. Right? The PC is going to determine this. But what we really are focused on is that we can actually test if this bit was set. Do we actually have a 1 set in the location, in bit location 2 of the RCC.CR register? That's what we'll be testing. So I hope this wasn't too confusing, but I hope it does make sense. And obviously I'm gonna show you how I do the modification in the header files. And yeah, that's it for now, and hope that you'll watch the next video. All right, goodbye.